Hey, astronomy people. Today I want to talk about supernovas and a couple things about them you might not know and why they're important. You've done the Supernova Computer Lab at this point. You've seen a PowerPoint and you went to a website. I just want to briefly talk about some of the highlights from that and talk about the two types and why it's important to distinguish the two and why one is actually more important than the other. All right, it's just the way it is. So I'm gonna skip over to the slides real fast and just show you a couple of the slides from the PowerPoint, and then we'll get to the nitty gritty. Okay, here we go. All right, so we got two types of supernova. Okay, so type one obviously is what we call a carbon detonation. So what that means is the star when it first formed was already massive enough. No, I'm sorry. That was not massive enough to fuse hydrogen, right? So it was considered a low mass star. Okay. Then somehow it was able to gain enough mass to start to fuse carbon. And once that happened, it went down a path where it eventually led to a supernova. All right. The second one called the Type 2 supernova, these are called core collapse stars because these are the stars that are already they were formed massive enough. The moment they began their life as a star, they were massive enough to fuse past carbon and eventually get to iron and eventually have what we call a supernova explosion. All right, so core collapse means it was always going to have a supernova. Carbon detonation means it wasn't originally supposed to have a supernova, but it stole matter from another whatever, and it got to a point where it was heavy enough to have a supernova. So let me show you a couple things about the Type 2, the core collapse supernovas, and then I want to go back to Type 1. Because believe it or not, Type 1 supernova are actually the more important types of supernova. They're the ones that actually give us a lot of helpful information. Type 2 are cool. Type 1 are super important for astronomers. So, you know, from somewhere in one of our target questions or something, that all stars, and by all, I mean that loosely, and that almost all stars will become a red giant. All right. And I say all because it's easier, but the reality is those really, really small red dwarfs, we don't really know for sure what they're going to do because we've never witnessed one die before. And then there are really, really massive stars that skip the red giant phase and just kind of go straight to a supernova. Okay. And actually, some of them are so big they call them a hypernova. But it doesn't matter. It's neither here nor there. Point of this story is for the most part, all stars will reach the red giant phase. Okay. Now, the sun, as well as all other what we consider low mass stars, will never produce enough pressure in the core to create a temperature that's hot enough for carbon to fuse with other carbon to make heavier elements. So low mass stars do not have enough mass to create a pressure to generate enough temperature for carbon to fuse, right? And that temperature happens to be 600 million Kelvin. All right. If you are more comfortable with degrees Celsius, it is also 600 million degrees Celsius. Okay. So remember each one of those. There's only a difference of 273 when it comes to Kelvin to Celsius, right? So at 600 million, there's basically no difference between the measurement Kelvin and Celsius. Just as a fun fact for you. Anyways, so really massive stars that are 8 times the mass of the sun or more, have the ability to fuse carbon into heavier elements. And what happens is kind of like what happens in the sun. When hydrogen runs out, the core began to collapse because gravity was squeezing it, and then helium ignited, right? Well, that lasts for about 2 billion years in our sun, and it lasts different amounts of times in other stars, but eventually the helium will run out, and all that's left is carbon in the core of that star. Well, if you have a really, really massive star, gravity will collapse it and collapse it and collapse it and collapse it till it gets to the point where the temperature is so high that now 6 protons that make up carbon and 6 protons from another carbon are moving so fast under so much pressure that when they smack into each other, they stick. As a result, they start to form heavier and heavier elements. And this sequence, these 4, carbon to neon, neon to oxygen, this is showing you how all the elements basically, and we're skipping over a few, but these are the majority, all the elements all the way up to iron are fused in the core of a star. Iron's the problem, though. Iron is the first element in the periodic table that when you fuse it, it doesn't give off energy. It actually takes energy in. Think about that for a second. Up until iron, every element, as it was fusing into heavier elements, was generating enough energy to push gravity back. Remember, gravity is always trying to collapse that core. Something has to stop it, right? And the fusion was generating the heat to push it back. Iron is not generating any energy. It actually takes energy from the core. That actually helps gravity. Now, gravity has a partner, and it helps it to collapse the core. Makes that sound, by the way. And it collapses the core even faster. And what ends up happening is really the only form of matter at this point with the pressure that is generated are neutrons for the most part. And what ends up happening is the neutrons get smushed down together, right? And fun fact about matter, no 2 neutrons want to occupy the same space at the same time, okay? Neutron degeneracy pressure, that's what that's called, by the way. So no 2 neutrons want to occupy the same space at the same time. So when they smack into each other, they hit back on each other with a force, right? And that bounce, that tremendous amount of energy from the bounce, the rebound, that is the beginning of the supernova. And all of the 2.7 billion Kelvin, the super high temperature, all of that energy that's stored in that core is now released to the universe. And it makes the most energetic event in the universe since the Big Bang. And I know if you did the PowerPoint, you know that a single supernova can be as bright, meaning it can give off as much light as all of the stars in the galaxy it's in combined, right? So it's insane, okay? So this is the shells of an onion here, right? And what you're basically seeing is that when hydrogen is fusing, the core is much bigger. And then hydrogen runs out, helium, the core gets smaller. Then it's carbon, then it's oxygen. Point of the story is as time goes on, the core gets smaller and hotter. And then iron is the problem, right? Iron core, we already talked about all this. Okay. So most energetic, I show you a bunch of pictures. Point of the story is it's a tremendous amount of energy. So what I want to talk about now is what is that other type of supernova and why does it matter? Well, the type of supernova I just talked about with you is actually the less common type of supernova. Right? Type 1 supernovas are actually more common. Type 1 is when you have a low mass star that gains enough mass to where it begins to fuse past carbon. All right. So here's the deal with type 1s. I'm going to explain how a type 1 works, and then I'm going to tell you why it's so important to astronomers. Okay, so a type 1 is it has to be in a binary star system. And that means there has to be more than one star in the star system, right? So that's why the sun will never, guaranteed never have a supernova, because there is no other star in our solar system, fortunately, for the sun to steal from, right? So what ends up happening is one star, the more massive star, will begin to die because the more massive star will fuse through its fuel faster, right? The bigger the mass, the shorter its lifespan. So the more massive star will begin to die. And what happens is it becomes a red giant. When the red giant happens, the matter literally expands 100 times away from the core than it used to be. That binary star, that other star, steals some of that matter from the red giant. Now, what happens is this makes the other star more massive. More massive stars have shorter lifespans. So what ends up happening to that second star is it begins to turn into a red giant. Meanwhile, the first star has a super hot core, really, really dense, super hot, not hot enough to fuse carbon yet. And what ends up happening is that original star begins to steal matter back, right? Because that other star is now in a red giant phase. But here's the thing. When it steals the matter, there's a critical limit. Let me give you this analogy, right? Bathtub. You close it in, you turn the water on, right? Whether you turn the water on slowly or fast, the water is going to fill up. But it doesn't matter. Once you reach the top, it doesn't matter if the water's coming out of the faucet really fast or really slow. The amount of water that's in the tub is going to stay the same because the rest is spilling over the edge, right? The point of the story is this. Every type 1 supernova is the exact same because they all have to reach a critical threshold. And once they reach it, once they get to that point, they start fusing carbon and they immediately start going down this path towards a supernova. As a result, every type 1 supernova that has ever happened in our universe pretty much gives off the same amount of energy. So that means if I know how much energy is coming out of a type 1 supernova and I see a type 1 supernova far, far away, I can actually determine its distance, right? You guys did this when we did magnitude stuff. We looked at the apparent magnitude, we looked at the absolute magnitude, and we were able to determine distance. This is the exact same thing, right? How bright does it appear from Earth? How bright is it actually? We know that because every type 1 supernova is the exact same. So type 1 supernovas are how we find the distances to other galaxies. That's why they're so important, and that's why I'm talking this long about it. Alrighty, folks, if you have questions on this, which I imagine a lot of you do, please write them down right now and see me, talk to me, join me during the live session on Thursday. Alrighty, folks, it's been a pleasure. Been a pleasure. Luke, if you're here, not a pleasure. Hasn't been. Okay, no. Sorry.